Okay, so while people are still streaming in, let me go ahead and start the introductions. So it is a great pleasure to have Yao here. So Yao graduated from Stanford in 2016. So I've known him for quite a long time. We overlapped while he was a graduate student, working with Risa, who's one of my longest collaborators. And Yao went on to get a fellowship at University of Pittsburgh and then an Einstein fellowship, which he took to Rutgers University. And then just last year, he started out a faculty position at University of Utah. And Yao is basically one of the persons that he's an expert on all things halos, halo structure, assembly bias, and in particular the halo galaxy collection. And so he's really a fantastic person if you're interested in cosmology, if you're interested in galaxy evolution. He straddles both lands very well and very proficiently. And so he's just a great person to talk to and just a really nice guy. So it really is a great pleasure to have you here. And I'm really excited to learn about your work.
Thank you, Laurel. Thank you for coming. That's super excited to be speaking here. When I was preparing this talk, there are just so many connections to things happening at Arizona in various ways. You will soon see. I know many of you through many different kind of connection, and some of you didn't know the joint connection with me. So I was really excited to be here. I had a fun day today. So I will be talking about low mass galaxies. This is commonly known as dwarf galaxy for astronomers' terms. I'm actually in the process of trying to now use the term dwarf galaxy. So I'm just going to call it low mass galaxy. I realized yesterday when I was talking to people that I also need to add the prefix of nearby, because now we have ZWST, which means we can actually see low mass galaxy at a very distant universe. But that is not what I'm going to focus about today. Well, I should say, feel free to interrupt me if you have any questions in between. I will start with actually the summary because, just in case I ran over, I'm going to talk about low mass galaxies. I will spend a little bit of time telling you why they're interesting, why they can tell us about the nature of dark matter and why they tell us about galaxy formation and evolution. And then I will tell you, well, dwarf galaxy, low mass galaxy, they are difficult to find and they are difficult to model. However, if you focus your observation on Milky Way existence, it's a little easier because over density. And so lots of progress on observation has been made in finding low mass galaxy around Milky Way existence. Now it's also a little bit easier to simulate because you can do zooming simulation and focus on specific systems instead of simulating larger bugs. However, when it comes to model, it becomes very complicated because now you have to model all the interaction between the satellites and the host and all sorts of things that we're going to talk about. So through the observation of this low mass galaxy in satellite systems and a lot of complication in the modeling land, model are being improved, and then we make progress in understanding galaxy formation and galaxy evolution through the interaction between the observation and the modeling. Now you might say, then why don't we just do field or isolated low mass galaxy instead? And so that obviously is a little bit easier to model because they're isolated, but observationally there's a lot of difficulties. But I will near the end of talk tell you some of the progress we have been making in finding low mass galaxies that are isolated. Right? So I will start with a movie that you probably have seen or similar version of it. This is the evolution of the universe if you can see dark matter. So what you're seeing here is actually dark matter only simulation. The light you are seeing is just a very clever color scale that we put high density into yellowish thing. They are not actually galaxies. So what you're looking at is the overdensity of dark matter evolve. The contrast become higher and higher as the universe expand. And you can see this high density region being formed. They are merged with each other. We believe the galaxies are forming within these high density regions of dark matter. As the universe is continuing to expand, you can see more and more contrast. You can see the fundamental structure of the dark matter. And this is what we believe the universe should look like if dark matter is visible. So this high density regions in the dark structure of the universe are where we believe the galaxies are living. So in a very high density region, we will have something called a galaxy cluster, which is a cluster of galaxies. So you can have a giant dark matter halo that goes to 10 to the 14, 10 to the 15 solar masses, and you host a bunch of galaxies in there. You can have a slightly smaller size of galaxy groups, which the dark matter component could have like 10 to the 13 solar masses. You also have a bunch of galaxies living there, and then you can have a slightly smaller, which has the Milky Way size system. The dark matter content there is about 10 to the 12 in solar masses. Now, one thing to remember is that the galaxy itself is really very much smaller compared to the dark matter structure that we're talking about. So when you are thinking about the Milky Way size system, the over density that people use Barre's theorem to put on a spherical object called dark matter halo, the size of that thing is about 10 to 15 times of the size of the galaxy. And by size of galaxy, in this particular case, I mean, the disk size. But roughly speaking, regardless the type of galaxy, the galaxy itself is much, much smaller. It's like about 1 order to 2 order magnitude smaller compared to the size of the dark matter halo. So and then you can also see that there are multiple high density regions in that plot. So that means even you have besides the central galaxy living in the very center, you could have other galaxies live inside the structure. So as physicists, we like to assume everything is spherical. So usually speaking, we would say, well, let's call this whole thing a dark matter halo. And so you will have a central galaxy live at the very center. And then you will have some other high density region, which we call subhalos. And you might have satellite galaxies living inside the subhalos. And the subhalos are gravitationally orbiting the larger halo, the central halo or the central galaxy. And that is also why they call satellite galaxies, satellite in the sense that they are orbiting the central galaxy. Okay, so this is a few terminology that I will use throughout the talk. So just want to mention that. So this structure that you see, I go through the galaxy cluster, galaxy group, and Milky Way size systems. It can continue to go down the scale, right? So you can go to even the smaller size. You might have a smaller central galaxy and smaller system, and so on and so forth. So here, if I put that on a plot, we have galaxies living in halos, and then I'm going to plot the halo mass on the x-axis and the stellar mass in y-axis. Roughly, it will look like this. So first of all, you see, there is a kink in this power law that roughly happen around Milky Way size. So the Milky Way size have a 10 to the 12 in halo mass, 10 to the 12 solar mass in halo mass, around 10 to the 11 solar mass in stellar mass. The low mass galaxy I'm talking about, broadly speaking, everything below that scale, I'm calling a low mass galaxy. Now, people have classified that into multiple different regions of low mass galaxy. It doesn't really matter that much at this point. But one thing I want to take away from this plot is that this connection between the stellar mass and halo mass is pretty well constrained down to about like LMC, Large Magellanic Cloud scale. And below that, we start to become more and more uncertain of what kind of galaxies live in what kind of halo. Okay, so if I'm going to take this plot and then replot it so that y-axis is the stellar mass divided by halo mass. This is what it would look like. It's still the same plot, but I'm just plotting the ratio on the y-axis. So first of all, you notice there's a peak that corresponding to the kink I mentioned earlier. It's around the Milky Way size. And then you can see we kind of have a pretty good, so the different lines coming from either different observation or actually different model framework to try to reproduce the observable universe. But you can see they're all kind of in good agreement in astronomers kind of standard, within like 1 order of magnitude difference. But they're all kind of within good agreement down to about like the Large Magellanic Cloud scale. And then below that, we basically either have no data or we are purely extrapolating our model to lower masses. Even from this plot, we have learned a lot about galaxy formation already. The fact that there's a peak and then this reversed V-shaped tell us about the feedback mechanism that's happening in galaxy formation. On the high mass end, we believe the black hole and the active galactic nucleus are responsible for preventing star formation to happen at this galaxy clusters, galaxy group, galaxy clusters. While at the low mass end, we believe the supernovae stellar winds are what is preventing low mass galaxies to have efficient star formation, and that is why you have this, this downward trend on both sides of it. So, okay, so I mentioned this. We have a pretty well constrained above LMNC, a lot of uncertainty still on the low mass end. Okay, so now why do we start this thing if they are so uncertain? Well, one of the reasons is that they are rich in dark matter. So as you remember this shape, if it's low, it means that the stellar mass is much smaller compared to halo mass, which means they are dark matter rich in those things. And so similar to why we are so excited about galaxy clusters, this dwarf galaxy also could potentially tell us a lot about dark matter. And so one way to do this is to look at how this small scale structure might react to different models of dark matter. So here is an example of showing cold dark matter, self-interacting dark matter, and warm dark matter. So the warm dark matter is very apparent. You can see there are much fewer substructure by eye, right? Like there are just much fewer like bright points. This is a dark matter halo. And so that tells you that the number of small galaxies you expect in this universe should be lower, should be fewer compared to a cold dark matter universe. Okay. Now, the self-interacting dark matter case is very difficult to see, but if you really squint, you will see that each of the smaller points is actually slightly less bright compared to the cold dark matter. So the core density of the substructure in a self-interacting dark matter case is slightly less dense. And that means you have a slightly shallower potential well, and then it also change the kind of galaxy can form in those halos. So it is a very subtle differences, but the basic idea is that potentially this could also tells you by studying the galaxies, tell you something about the underlying dark matter property. So here is a more specific case for warm dark matter. So you can really ask, consider different dark matter models. So we have cold dark matter, so this is ratio to cold dark matter. So cold dark matter is the 1.0 horizontal line here. What is this transfer function? Roughly, you can think about what is the suppression on structural formation as a function of halo mass. So roughly speaking, 0.75 means that you suppress about 25% of the structure forming at that mass scale. So I'm showing you a few different dark matter model with some specific parameters. So this is not saying all warm dark matter have that line. Obviously, if you tune the parameter, you can have different lines. But the basic idea is to tell you that you can pick a dark matter model, you can plot this, and you can ask, can I find in this universe, say 10 to the 7 solar masses halos? If I can find a lot of those and they are not a statistical fluctuation, then you can rule out that purple line, for example, with that specific parameter, right? You cannot rule out all fuzzy dark matter, but you can look out the specific parameter going to making that purple line.
Question.
Yes.
What is the y-axis exactly? What does this mean?
This is the transfer function relative to CDN. So what does it mean? It means it's kind of like the power spectrum in a way. Does that make sense? So really, that function is a function of wavelengths you're doing the Fourier transform, and then we are just the halo mass is really just what is the typical halo mass for that wavelength. So that is one way you can do that. There are other things that you can do to distinguish different dark matter models. So one possibility, this has not really been done observationally, but theoretically, the distribution of this low mass galaxy in a satellite system could potentially also tell you something about dark matter. So you can see compared cold dark matter and warm dark matter, you more or less just have fewer points. Each of points is galaxies that we predict to be there. But if you compare the self-interacting dark matter, which is the third panel here, you will notice that the distribution is more asymmetric. And that is because in this particular simulation, we included the large Magellanic Cloud, which is falling into Milky Way. And if there's self-interacting between the dark matter, it will create pressure and then actually more likely to reduce the substructure along the orbit of the LMC. So that is another possibility that you can use to study the different models of dark matter. So these are just examples. To be honest, we are still kind of far away to be really able to using, for example, this specific case to say, well, how can I put a constraint on the self into the dark matter? But I think, I'm confident that in the next few years that you will start to see papers using these kind of ways and say, well, here's the constraint we derive. Okay, so the low mass galaxy, if you remember from earlier, it spans a very, very wide range of stellar masses, which also means they have a lot of diversity in terms of their morphology, their stellar content, their color, their star formation rate, etc., etc. So having a wide range, been able to survey a wide range of low mass galaxies can really help us to get an understanding about galaxy formation and evolution. So here I'm just showing you a few, different low mass galaxies. Next to and Rectangular 2 are both satellite galaxies in the Milky Way. You can barely make out the Rec-2 dwarf galaxy. They look like individual stars. It's very, very low mass. You have the ultra diffuse galaxy. This is, very massive for dwarf galaxy scale. It's kind of like LMC or even slightly above LMC mass, but it's so diffuse that it looks like a dwarf galaxy. And then you have, I will talk about Saga in a bit, but you have like this kind of blob that is uninteresting. It's not a beautiful spiral galaxy, but they actually are also like small galaxies. They're orbiting larger systems and tells us a lot about this formation of those small things. So as I mentioned, so here's the motivation part, if you remember my flow chart at the beginning. So now I'm going to tell you that, well, they're difficult to model. We have very limited knowledge and require high resolution simulation to simulate these things. And they're also difficult to observe because they're intrinsically faint, they're low mass, so require deep observations. So I'm going to start with the observation side first. So they are difficult to find because they are faint. That is a little bit simplified things a little bit too much. Because you can, you can always build bigger telescope and go to deeper and deeper, right? But they are not just faint so that they are difficult to find. Part of the trouble is that we are beating with a large volume of your background. So you see a faint object. It can be either intrinsically faint and they are close, or they are intrinsically bright, but they are further away. Now, unfortunately, when you look out as a light cone, you have a much larger volume in your background compared to things that are near to close to you. So what is really difficult is to distinguish something that appear faint to you, whether they are something that are nearby or something that's further away. But unluckily, most chances there are things that are further away because of volume difference. If I put that into numbers, so for example, if you have a survey that have a limiting magnitude at, I don't know, say 18, so that is roughly SDS's main galaxy survey. So per square degree, you only have about 1 galaxy that is within redshift less than 0.02. But you have your total galaxy you can see is about 200 galaxies. So you are finding 1 galaxy across 200 galaxies in that field. And this problem becomes more and more significant if you go down to say 21st magnitude. You are still at about 1.5 galaxy less than 0.02, but now your background galaxy jumped to like 3,000, right? So you are finding a very, very small population in a very large population. And this is going to be worse and worse as we now welcoming the new surveys, including, DCAN, DS, DESI imaging, and LSST. So what do we do? Well, satellite system is a good place to start because we know there is overdensity and the central galaxy is much brighter, right? So we usually already know where the central galaxy is. And because we expect this small galaxy is orbiting around the central galaxy. So if I can identify the central galaxy, I can just look the vicinity of that central galaxy, and then more likely I can find the low mass galaxies there, okay? And so that is an illustration of like Milky Way and Milky Way satellites. Simulation-wise, is also a good place to start because I can put I can simulate a low resolution cosmological box find, again, similarly, those larger galaxies, and then put much more particle in that region and do a zooming simulation. And that will also resolve the smaller galaxy. So actually, both in terms of observation and simulation, it's always it's actually a good idea to go to satellite system to find these small galaxies. So in the Milky Way, for example, we have been using this method to find the satellite galaxies in the Milky Way and actually try to derive constraint for dark matter properties. So here, we are looking at Milky Way satellites, which are the stars discovered by both Diaz and Penn stars. What we are plotting here is the stellar mass halo mass relation, as I told you earlier. So you can see, like for example, this point means that you have a galaxy is about like 10 to the 4 in stellar mass, 10 to the 9 halo mass. So now what we can do is we can go to the lowest point on that plot, and then we say, well, that means we have a dark matter halo that is about 5 times 10 to the 7. And then we can compare to that, and then we can put specific limit on the different kind of dark matter models. This constraint is still not super competitive compared to other constraints that we have gotten on the same dark matter property. But you can imagine as you discover more and more, faint galaxy, our constraint will become more and more competitive. But our constraint could also become more competitive if we can shrink the error bar on this plot, right? Because when we are ruling things out, we don't just rule things out. We rule things out, say we are ruling things out at 95% confidence level, and then we need to take the error bar that you're seeing in this plot into account. So if there's some way to shrink this, we can also get a better constraint. The other thing you might notice on this plot is that there is a dashed line there, and our stellar mass halo mass relation is kind of deviate from that line. So that also tells you that already at the Milky Way region, we see that the best fit stellar mass halo mass relation deviate from, if I just extrapolate from a well-known stellar mass halo mass relation. Actually, this is from Peter Brusick, which is also, well, he's not here right now, but he's also faculty here. We also overlap at Stanford. So that is also like very interesting, and we'll talk about that a little bit. If you pay a lot of attention to this plot, you might also notice the word visit on the C there. And so we actually noticed that if we didn't take into account the existence of LNC, we actually cannot model the Milky Way satellite population. So we know that the LNC actually has a significant contribution to the satellite population in the Milky Way. So all this is telling you that there is still a lot of uncertainty that we need to kind of take care of in order, even though we can already derive constraint, in order for our constraint to be competitive, either we need to discover more low mass galaxy that is really, really faint, or we need to better understand our model and reduce our uncertainty in the modeling component. So that's basically what I just said. Okay, so how does this model really works? So we basically start with a zooming simulation, right? So we simulate this kind of Milky Way systems, and then we apply a galaxy halo connection model, so connects dark matter halo with galaxies. So the simulation have only dark matter halos, and then we put a galaxy in through a galaxy halo connection model. And then we do a forward modeling. So you can say how I will observe those things. So you observe using your observational selection function, and then you then calculate likelihood and then iterate through a Monte Carlo process. So throughout this process, if I just start with a regular zooming simulation that does not have an LNC, you will basically just get no good fits. And so that is where we realize, okay, LNC is really important, so we need to beat this process. So you can see one of the biggest uncertainty here is really the galaxy halo connection model in this second step. Like, how do I put galaxies into halos? And how do I really understand the uncertainty that we have in there? So there is a wide range of levels of galaxy halo connection models. You can go all the way to actually run the fully hydrodynamic simulation, which is still not first principle because you don't actually resolve individual stars. So you still need to put in some empirical prescription in there. You can all go the way to halo occupation model, which really is a very large scale description that tells you at a given halo how many galaxies you might find. So there's a wide range of things they can do. And so theoretically, if I were to kind of abstract what I'm talking about galaxy quantum model. I can think it as if you give me specific halo properties, which I wrote here, X halo 1, X halo 2, how do you predict the distribution of galaxy property that you're interested in? So I'm predicting a probability distribution of galaxy property 1, galaxy property 2 as a probability distribution because there might be some intrinsic randomness that you can never model. For example, right? The universe might decide that the galaxy formation is not 100% deterministic, so maybe there's some probability, right? The challenge here is deciding what property to put in, to use in this thing. So some of you might have heard subhalo balance matching. If not, it's okay. If not, ask Peter. But basically, you choose, say, subhalo mass, stellar mass, and then you are asking how these two things correlate with one another. You might have heard of halo occupation distribution. So in this case, you use just host halo mass, and then you only ask a very simplified thing, as the number of galaxies as your galaxy property, right? So you are doing this kind of very simplified assumptions. Now, I should say both of these models are still the most widely used models even nowadays. But you might ask, is this really enough? Don't we need other halo property in here? First of all, we obviously need other galaxy property if you want to really reproduce a realistic universe. But let's say I'm going to satisfy myself with just stellar mass and number of galaxies. How do I know that just the halo mass is enough, that I don't need other things? And if I'm giving this talk like 5 years ago, I would need to spend another like 20 minutes to convince you that, yeah, we indeed need other things. And nowadays, people really kind of, understand that there should be some other secondary dependence on other halo properties. So for example, we believe the halo from early tend to have a higher stellar mass at a fixed halo mass because they have a little bit more time to accrete stellar mass. This is sometimes referred to galaxy assembly bias. We also know that halo form at the same halo mass, halo form early, tend to have fewer satellite galaxies in that dark matter halo. And the idea being the satellite galaxies have more time to merge with the main galaxy. So basically, the satellite galaxies merge with the main galaxy, deposit the stellar mass onto the main galaxy, and disappear. So you have fewer satellite galaxy, but more stellar mass at the central galaxy. Okay. How much of this we have actually observed observationally is a hugely debated question because the promises is at fixed halo mass, and that is the hardest thing observationally to control. It's super difficult to have a fixed halo mass control example. So a lot of research is still going on in terms of observationally confirm these things, but there are recent projects actually. Just I think last week there was a paper on like trying to show this with STASI 1 degree data, 100 degree data. But definitely have been confirmed in many high-yield simulations. So the reason I want to mention this is it means that whenever we do things that require you even the simplest form of galaxial connection, right? I'm just literally just doing number of galaxy and stellar mass as a function of halo mass. There could be like unexpected correlation that you might need to take care if you want to do precision, either it's cosmology, constraint of dark matter things, dark matter properties, or whatever. So here's a few examples. Milky Way satellite, I already mentioned that. Imagine you want to do substructure strong lensing. So this is trying to find perturbation of Einstein ring. So there, you kind of need to know what is the probability of finding a substructure given your system, your lens system. But you know your lens system through the measurement of stellar mass. So without assuming that correlation, and with assuming the correlation will actually give you a different prediction of number of subhalo you might expect. Now, many of you should know, Elizabeth probably have talked about this many times, that there is a lot of systematics in cosmology measurement. And that also, some of it also coming from this correlation. And because this is particularly prominent at small scale, a lot of time we have to basically cut out small scale data because we just still are not good enough in modeling those correlations. Okay, So I'm half time and I'm halfway through my slide. I'm very impressed with myself. Any questions so far?
So, so you're trying to connect properties of halo to the properties of the galaxy. So if we change the type of dark matter, then what property of the galaxy is most likely to be affected?
Yeah, great questions. We don't exactly know. But for example, if you change the self-independent dark matter, we believe the galaxy, say, rotation or their light profile could be affected because that is how the dark matter profile being affected. People have been trying to do simulation, like so people will do hydro simulation combining self-independent dark matter and warm dark matter. One of the tricky things that we don't really know is that whether there's additional coupling between the dark matter model and the baryonic model that you put in. If not, then most of the time it just reacts to the final halo composition for the most part, right? Because really what happens is that the dark matter halo start to form first, and then the potential well is established, and then gas start to cool down within the potential well. So most of the part is just responding to the potential well from the dark matter. Now, if there's additional coupling with the baryonic and dark matter, then it's a different question.
Yeah, I wanted to ask a question out of pure confusion. So one question always comes up with things like this is what the joint distributions look like. That is how much scatter is, just to pick your top relationship, stellar mass with halo mass, how much scatter is in that. And the thing that's confusing me is a number of slides back for, I think, our Milky Way, you showed what looks like an incredibly tight relationship between, yes, by me, that looks like a pure one-dimensional relationship that I could take stellar mass and just read off a halo mass, that there's actually very little room for there. And that's what's, as you can see, a source of confusion because it looks incredibly well determined.
Yeah, that's a great question. Well, so it depends on, I guess, large and small is relative, but let's read off the plot. So if I know the halo mass, this model predict at 2 sigma about like a full order of magnitude.
Well, I'm looking at your data points though, which not show that scatter.
Oh, sorry, the data point is just the best fit points, right? So data point doesn't show the scatter.
Okay, so is there some distribution, real data?
Yeah, so that band is the band is trying to show the uncertainty.
Okay.
So that is why I also say like this point contribute to the constraint, but to really get a constraint, we have to take this horizontal scatter all the way into the constraint. So it's not that well constrained.
Okay, so what I'm missing here is just this basic plot of determined halo masses versus stellar masses, so I can see what the real scatter is.
Yeah, so in this case, it's the band. So roughly speaking, I would say it's about 1 order of magnitude difference. In this earlier plot, all this individual line roughly is also the median relation. And there is a gray band here. You can see it's roughly it's a typical scatter, but that is a statistical scatter. And then there's a systematic scatter that's between different lines. If you combine both of those, it gives you still about 1 dex. So like a full factor of 10 uncertainty. If you want to say even within 2 sigma. So it's a pretty large scatter.
Right, it'd be great just to see the basic data though, without fits or anything else. You can see what it looks like.
Yeah, well, so the individual data point is a little different, right? It's like just to be very clear on these things, we are not measuring individual dark matter halo masses. That is not possible at this low mass scale. Like for very large galaxy clusters, sometimes we can, measure the individual systems mass. So this is all inferred by the model.
Okay.
So it's a joint function. Yes.
When you're doing the zoom-in simulations and looking for Milky Way-like galaxies, are you looking for just or halos? Are you just matching mass, or are there other properties that you're trying to match?
Yeah, great question. I will answer your question in a few slides.
Oh, okay.
Okay, so now, after everything I told you, you might then ask, well, you just showed me this nice thing of using Milky Way satellite to constrain dark matter. But then you also tell me that, well, all these host halo properties affecting your satellite population. So what if our Milky Way is somewhat spatial? So in particular, as we talk about, our Milky Way has the largest homogeneous clouds. And the question is, do we not worry about that our interpretation of the Milky Way itself might be biased because, spatial history or spatial population in the Milky Way? So there are basically kind of two ways you can address this. So one way is to kind of get a better understanding of our own Milky Way, okay? And this actually hasn't been possible, I would say, maybe 5 to 6 years ago. But now with Gaia, we have very, very detailed mapping of the stellar structure of Milky Way. And people start to know what is the previous merger event of the Milky Way. And so one thing that we have been doing, this is with a student at Stanford and also a postdoc at Colloquia. We're doing this Milky Way East simulation. We basically trying to do a zooming simulation that with a recent accredited LMC and also with the Gaia Enceladus sausage merger event in the past. And that means we will have a range of population that match Milky Way in other than halo mass, but also in these two ways. So this is one of the things that we could do. Now, what is Milky Way East? Obviously, you can define more and more criteria, and they will add, like as we start to understand Milky Way more and more, we might be adding more and more criteria. But that's also why we simulate a range of things that both have those events. And then what we can ask is like, is the subhalo system look different? I'm not going to spend too much time talking about this. Roughly speaking, you are looking at the subhalo mass function on the top and subhalo radius distribution on the bottom. The purple is the Milky Way simulation. The black is the typical mass selective sample. And so you can see there's systematic difference between just a mass selective sample versus if you select on specific historical events of the Milky Way. So this is kind of a recent work. We haven't published this yet, but we hope it will be soon. But the idea is by understanding the history of the Milky Way, we might be able to get a better constraint, a better matched simulation as our base. Okay. So that's one way you can do to understand where the Milky Way is spatial. So the other way you can do is to Milky Way in a broader sample. Okay, so that is the opposite way, I would say. So one way is to understand more detail of the specific object. The other is to compare the object with the population. So for that, we kind of started this thinking about, well, is the Milky Way spatial? And then try to answer this question. And this project started almost a decade ago called the Saga survey. And Ben actually is one of our collaborators. We have a lot of data actually taken on MNT here. So the idea is to find Milky Way mass galaxies and then survey their satellite population. Now, if you remember what I told you earlier, the central galaxy is much, much smaller compared to the dark matter halo, right? And then you find the satellite population, you need to look throughout the halo radius. So what we do is we find a bunch of Milky Way mass galaxies, we draw a circle that roughly corresponding to the halo size, and then try to find the low mass galaxies in those regions. So this is difficult because the reason that I mentioned to you earlier, you draw a circle around the Milky Way mass galaxy, you look at all the galaxies down to your survey limit, you find thousands of galaxies, most of them are background galaxies. If you put a fiber on that, for every galaxy and measure the redshift, it will take years before you can get a statistical sample. So we need something to help us. So photometric information provides some sort of information about how close the object is, right? Very simply, if you have something that's really, really far away, it will be so red that it just cannot be a low redshift galaxy. So that is kind of the easiest way you can do. That's what we did in Saga stage 1. We just do a very conservative color cut since they completely cannot be low redshift galaxy. But that still leaves us about 1,000 objects per square degree. And then we start to incorporate other things like the size of galaxy and other information and kind of improve that to a smaller candidate. But to that degree, we really cannot reduce it more. And then we really need to have follow-up with spectroscopic measurement in order to find the actual satellites. If you don't think this is really difficult, here are the 5 objects that I picked from the green points, and only one of those are actually satellites in there. Okay. And then you can mark your answer. You don't need to tell me. I will reveal at the end of the talk. Okay, so we have published this survey twice, our first and second data release. But now we really already have 102 hosts that we have surveyed. We have almost 400 satellites we have identified. We are wrapping up and do our data release 3 paper. But it's really exciting because now we have 100 Milky Way-like system that we can compare the Milky Way with. This slide is really just to show you the pretty image of all the satellites we have identified. You can see really bright things like LMC or even brighter than LMC kind of satellites to all the really faint, fuzzy blob that, some of those it's barely visible on this screen. There is really a wide range of low mass galaxies that we identified in the systems. Each of the groups you can see that is circled by each of the color lines means one system. So you also see there are systems with like 9 or 10 satellites. There are systems with only 1 or like even 0 satellite to the survey limit that we have surveyed. So if I take this and then plot the luminosity as a function of numbers, I can build, let me come back to this later. So I can build the satellite luminosity functions, right? So this is just the satellite function numbers. I put the Milky Way in there, which is this dashed black line. So Milky Way is kind of typical in terms of the number actually compared to the Saga sample that we have seen. Actually, this is from our second data release. So I didn't even put 100 lines on there. It's actually barely visible if you do that. But one interesting thing from even just doing this plot, or if I put 100 lines on there, what you will see is kind of a very clear color gradient. And that is actually itself very interesting because that means the thing I told you earlier about galaxy, like larger galaxy living larger halo, it's not completely wrong. The scatter between the galaxy luminosity and halo sizes are not completely stochastic because otherwise it would kind of erase this thing that you are seeing, right? So it's saying that the halo mass function that we are seeing in simulations are to some extent preserved when you look at the satellite luminosity functions. The scatter is not enough to completely erase the this kind of color gradient in this plot. So coming back to this, Japanese Saga survey, like at the very first slide, I told you that lots of progress has been made in like surveying Milky Way systems. Saga survey is definitely not the only one. So, in the Milky Way and the 31, we have found lots of satellites. People also have been trying to do this in the local volume, so within 20 megaparsec. There, you can't really do redshift as a way to measure distance because the local flow is too strong. So usually you do like a surface brightness fluctuation or tip origin branch to get the distance measurement, get the satellite population. And then once you go to the Saga region, you get more samples because it's a larger volume. But obviously you see fewer satellites because they are further away. If you go to SDSS, you can also do this with SDSS, but you usually only find 0 or 1 satellite in the system, right? But this is kind of like the landscape that we have in terms of finding satellite around Milky Way system. So you can then now compare each of the luminosity lines with simulations or with model prediction. So the band that I'm showing you on the left, the steps are still just taken from 6 systems on this plot, and the band is like a model prediction. Okay. So roughly speaking, they're like kind of consistent, but you can kind of see like in some cases the model doesn't seem to make I would say like one thing you think is like the model difference between these 6 hosts is much less than the actual observation. So there was some hint that the model does not provide enough variance across different hosts that we can see. So one thing that we were asking as we are modeling this is like, what is the missing ingredient in terms of the modeling tool? So it turns out, if we just look at the satellite number, it's not a full picture. You also need to look at some of the property of the satellites. So one thing you can look into is something called whether the satellite star forming or quiescent or quenched. So here I'm showing you the quench fraction from the Saga sample as a function of stellar mass. So this is just saying that at about 10 to the 9, there's about 15% of the Saga satellite they are quenched. At 10 to the 7, there might be about like 70% of the Saga satellite they are quenched. I'm also showing you a comparison with the Milky Way M31, which is the orange points, and I'm also showing you like field galaxies. Okay, so you might say, why is this important? So first of all, you want to ask, can the simulation and the galaxy connection model that I mentioned can reproduce these things? So let me take a look at the hydro simulation first. Hydro simulation kind of can reproduce. This is exactly the same plot, but in hydro simulation for the n-body shot group. So you can kind of see the kind of span kind of a range of things in that ballpark. If I move the green points this plot, they roughly line up. But it's such a wide range. So what is explaining this scatter? There's actually not very clear understanding yet, because there's only 4 simulations on this plot, and it's difficult. And that is where the galaxy halo connection model I mentioned is really useful, because we can do that much in a much computational cheaper way, and so we can look at a much larger system to study that. So let's see. Okay, so one thing that we have been trying to do is to take the galaxy connection model called the universal machine that's developed by Peter Bruzzi, and ask, can we use universal machine to reproduce what we just saw, what I just showed you from the quench fraction? Okay, and what we found is that you cannot unless you start adding new model components. I'm not going to have enough time to actually tell you the specific model component, but basically you need to modify how you model the quench object, and also how they correlate with the star formation rate. But my main point being, like, you could make a prediction from the universal machine, give you the correct satellite luminosity function, but wrong quench fraction. So this is from the universal machine. We saw the added model component, and you can see the prediction, which is the blue band there, is inconsistent with other predictions from the previous observation. Sorry, previous galaxy collection using this model. But if you look at the quench fraction, it just goes to 0 at low mass, which we know is wrong. Like, we know observationally, this very low mass galaxies, at some point they must be quenched. Actually, we believe the quench fraction should go to 1 at some very low mass. So this is saying that despite this being completely wrong, you can still get the stellar mass halo mass relation kind of right? And so there is this additional modeling component you kind of need to worry about if you want to reproduce some specific thing in your observation. And in this case, the specific thing is the host interaction that is difficult to be captured by this model. So I'm going to show you a very complicated plot, but bear with me. I'm not going to go into detail. I just want to focus on one thing. There are 3 dotted lines here, red, black, and blue. This is the universal machine. We saw the added model component, and it becomes the solid line, red, black, and blue. This is when adding the model component that I skipped, and you can see that expand. So the different lines trying to match different halo environment. The red is being satellite environment, and the blue being field galaxy. So we're adding specific model component to push the difference between satellite objects and the field galaxy in order to match this very low mass regime. But you can see even with this improved model, it's very difficult to match at this slightly higher mass regime. So we are still working on this, and the message I want to convey here is, like, to model the satellite system, you cannot just take the simple galaxy connection. You really need to model how the host environment, it may not be just the host property itself, but also by the environment of the host, impact the satellite population. And to take that into account, your model needs to be flexible enough so that you can actually match both the field galaxies and the satellite galaxies at the same time. And that is not at all trivial, even with universal machine, which is already a very flexible galaxy conjunction model that you can use. Okay, any questions? Yes.
This is very interesting, but I guess I was wondering how in this Saga survey you correct for the duty cycle of being able to see a satellite. So I presume that there's a lifetime for each satellite coming in until it gets merged in perhaps with the parent object. So do you apply a correction when you look at the numbers, or are you just taking the raw numbers as you see them?
We just take the raw number, but we also comparing to a snapshot of the simulation, right? So in the simulation, we also, it's like you take a snapshot, so you are not like considering things that was following or after it falls out. So I think it's a fair comparison in the sense that you are also doing that in your theory part.
So a related question would be, do you see a difference then based on the, if you divide your sample into two for each host, are the ones that are at larger radii somehow distributed slightly differently in terms of the number per mass compared to the ones that are closer, like well within an interaction distance?
Oh, yes, and that is actually this one. So the quench fraction is there is a significant trend as a function of how close the satellite are to the host. So the red are the data points, and you can even see the model effect is dispensing. The model doesn't really reproduce that significant dependence as much. So in a way, the model is still trying to capture the host interaction, but not quite there yet. Yes.
So when you first show the Saga survey, you have many like background galaxies that are distant.
Right.
So what if one of your satellite galaxy gets misclassified in that stat because you have very few satellite galaxies? So do you like evaluate the accuracy rate of rejecting satellite candidates?
Yeah. So there are two things: you might miss the satellite galaxy, or you might take a background galaxy as a satellite galaxies, right? The purity and the false positive or false negative. So we take both into account when we compare it to. So when we compare the theory, we actually take both into account. So basically, you do a forward modeling observation in the theory then.
What's the criteria to sort the Saga galaxies into forming?
In this particular case, we basically do, well, it's a little bit complicated. So if there is a clearly emission line, we just say whether there's an emission line. If there's not clear emission line, we see if we can detect an UV, and then we calculate star formation rate, and then do the same star formation rate count, which is like 10 to the minus 11. Sorry, specifically star formation rate 10 to the minus 11 as the count. Okay, so okay. I'm a little bit out of time, but maybe I can do this. So you might just ask, why don't we just redo this with field galaxy? Then we solve all the problems. Like we're spending so much time talking about galaxy halo interaction, host satellite interaction, all this complication going to the galaxy halo conjunction models. Why don't we just do field galaxy? Well, because it's very difficult to find that, right? Because you don't know where to find, and it's difficult to find those field galaxies. Now you can do this in two ways for field galaxy. You can have a better SDSS and then find those things. And that is being done. We have DESI, and DESI is going to find a lot of the satellite systems, even with their bright galaxy sample. And that is super exciting. You can also try to find isolated dwarf galaxy in the nearby region, because that allows you to find, remember, you want to find the smallest galaxy, right? And that, well, DESI will not give you those because they are, looking at further away. So you can also find very things that are really nearby. Okay, so for things that are really, really nearby, we have been trying to identify galaxies that are slightly outside the Milky Way and Andromeda, and try to see if they are, if we can find any of those. So far, we find 3 objects actually. So this is Pegasus W. This is what it looked like in DESI Legacy Imaging Survey. That's the same field in Hubble Space Telescope. So you can see the galaxy kind of like individual points of the galaxy. We did find this through the DESI imaging. There's kind of diffuse light there, but we follow with Hubble. You can see a nice red giant branch. We can estimate distance, and things like that. This is a 10 to the 6 times 10 to the 4 solar masses object. And later we find two more. So this is Leo M and Leo K. Again, Hubble image in there. You can see the very giant branch. This is even slightly lower mass. It's about 1 times 10 to the 4 solar masses, about 400 kbc there. So these are really exciting. This is kind of the very first few super low mass galaxies that we found outside of the dark matter halo of the Milky Way MN31. And then one interesting thing that you can ask is, are they really isolated, right? Because what we want to do is to use this galaxy and do all the dark matter stuff, but we need to first make sure they are indeed isolated. So unfortunately, even though they are like technically outside the dark matter halo, they are like not quite isolated. You might have heard something of splashback radius about like how galaxies can get influenced by dark matter halo even they are still outside the viral radius. And it's kind of the case in these things. So particularly in Pegasus W, you can see this is cumulative star formation rate history. You can see the star formation didn't really completely shut off during the reionization. There's still star forming, and it really shut off around H1. And we believe that is around the time this object is passing through M31 and shut off the star formation. For Leo M and Leo K is more complicated. It looked like they are being, quenched by the reionization, but they are really close also to the Milky Way. So it's really very difficult to rule out completely. There's no environmental effect on those things.
Sorry, what is the vertical axis? It's not labeled.
Oh, right, sorry. It's just 0 to 1, which means like how much star has formed. So 0% and 100%. So this means you form 90% of your stars at this time. So this would mean that most of your star has formed right after reionization. And then for the remaining time of the universe, you only form about 10% of your star. So in the case of Leo M and Leo K, you might argue they are quenched by reionization. It's a little bit ambiguous, but maybe. And all the different lines, just different models. There's systematic uncertainty doing these things. For the case of Pegasus W, pretty clear that after reionization, it only formed about half of the stars, and it still continued to form until interaction with M31. Okay. So just to show you where they are, Pegasus W is right here. It's like right outside M31 star matter halo. That is the dash line. And this is Milky Way, and we didn't put the Milky Way thing, but well, because this is the Milky Way coordinate, so 300 kbc is here, so you can see that they also kind of right see outside of the Milky Way dark matter. And so it's kind of like we did this search, we didn't know what the distance after we do the Hubble follow-up. So obviously we cannot predict how close they are to the Milky Way halo to begin with. But so it's kind of unlucky that all three objects that we did our first round of observation, they are all kind of still close enough to the halo. We actually have six other candidates in queue. Hopefully they will be observed this semester, and then we will see how they are in terms of where they are. And then I'm personally very excited that we might be able to find really isolated objects and can ask about their star formation history. Yes.
Do you have any kinematic information about this?
Yeah, we're trying to follow up, but yeah, we didn't actually get successful follow-up proposal. It's too expensive, and yeah, the tech doesn't want to spend so much time on a single object. But it's definitely on the list.
What are the different color lines?
It's just a different model to infer the star formation history from the color magnitude diagram, and so it kind of represent like model uncertainty.
You looked at quenching mechanisms for lower mass galaxies too, such as satellites around like LMC analogs?
Sorry, quench mechanism for low mass galaxies?
Yeah, quenching mechanisms for satellites of lower mass. So these are satellites of like a Milky Way type system, right? Have you looked, or do you have plans to look at hosts that are smaller in magnitude?
So this right. So this might become satellite of Milky Way, I guess, right? They might have flyby. We don't know. But you're asking about satellite of LMCs, for example. Yes. So I guess I don't have data on those things. I mean, there's definitely a very popular topic that people are looking into. Is the environmental quenching is probably still effective even at LMC scale? I don't know about if you go to even lower mass. But the galaxy itself mass, the mass of the satellite itself is all important, right? Like if you are talking about like 10 to the 4, then reionization might still be effective. So you didn't have a chance to get environmental quench because reionization did that first. Okay. Since I'm basically run out of time, I'm just going to show you 2 quick slides, not a lot, but just to say, to find isolated galaxies in the field, not even near the Milky Way, one thing you can do is do machine learning. So you can take all the galaxies, you put in machine learning. It's kind of a photo Z, but specifically for very, very low resolution. We have been trying to some of these methods and putting this into the spare fiber program of DESI, and we should get a quite a good number of low redshift galaxies. The orange curve is what we got. This is not like super lowest mass galaxies that we can find, as we discussed, but it's a very nice sample to compare, even at the 10 to the 8, 10 to the 9 stellar masses to understand the comparison between field galaxy and satellite galaxy. And also collecting more of these dwarf galaxies, the other ambitious goal of ours is that we can do dwarf galaxy, low mass galaxy lensing. So we want to stack all this low mass galaxy and use them as lensing kernel and see if we can make prediction. We predict that we can do that with LSST, but that is with year 10 data. This prediction is with year 10 LSST. Now there's a lot of things that go into here. How do you make a selection without redshift survey? How do you make sure that you don't have contamination for higher masses? So a lot to be sorted out, but we have been doing this with some precursor data, and I think there will be some exciting results that we are already seeing, and hopefully will be out soon. But basically, we can do photometric selection on potential low mass galaxy and try to see if we can get a halo mass measurement from the lensing sample. So I'll just give you a teaser there, and hopefully more will be coming on that note. With that, I will just show you my summary slide again, and thank you for your attention.
We've had a few questions, but let's try 1 or 2 more.
Right, so I'm curious, so Euclid is flying and it's high resolution imaging capability of white area. Roma is a few years in the future, but I'm wondering, it seems to me that these would really crack this problem pretty well for you, since you'd be able to resolve the distance ambiguities in your samples. Is that so, or have you thought about that?
Yeah, a little bit less on Euclid, more just because I didn't have collaborator in that circle. But yes, it will. Part of the thing that we're doing with DESI is on a similar event is like getting some redshift sample as kind of training data, and then we can use that in more wide photometric. For Roman, Roman is actually quite exciting that you can also do partial resolved population quite well. So that means you can have a dwarf galaxy that are nearby, only have a few stars you can see, but you can kind of do surface brightness fluctuation kind of thing with Roman. And it's large enough sky area that you can basically like in the right mass range, which is about I think about 10 to the 4-ish. You can basically get as many as dwarf galaxy as LSST can, even though it's a smaller sky area. But just it has a better way to partially resolve the population.
Let me suggest we do 1 more question, and then afterwards people can come in and talk to. Yeah,
There's one online.
Oh, there's a question online. Oh, I didn't. Yes, online. I'm not sure who. Okay.
Okay.
Sorry.
Okay. Thanks for a great talk. I was just wondering, when you were showing the star formation histories of a few very low mass galaxies, how confident are we about whether the host halos of these galaxies have already existed at the reionization era?
You mean in this case, the 3?
Yes, for those Leo galaxies, for example.
The host galaxy are Milky Way M31 in these cases, right? So the Pegasus W is supposedly falling into M31. Leo and Leo K are supposedly, either flyby or falling into Milky Way. So they are. What was your question? Sorry.
I'm sorry, I was talking about the host halos for these low mass galaxies, like the satellite
you mean-
halos.
Right, you mean how their host halo, whether they have formed at the reionization?
Yeah, right.
Yeah, we don't know. So that's, I mean, connected to kinetic question, like we need a handle on the halo masses. So far we don't, right? Like I can do a Galaxy halo connection model and say roughly what the halo mass is, but that would not be accurate. So if we can get some kinematic measurement, we can get a halo mass, then, you know, from simulation, we can predict how likely they have already existed at the reionization.
Okay, thanks.
Okay, let's thank our speaker one more time. By all means, feel free to come and ask more questions.
Not too bad.